I am Chandrasekhar Gupta and we are discussing programming concepts. I want to congratulate each and every one of you for moving this so far. We have almost completed all the topics that are required in C programming or any sort of programming language. It's the right time for us to take a dive into data structures. There are many data structures, linked list, stacks, queues and so on. But everyone faced difficulty with them. We'll try to figure out an easy way for each and every one of the data structure and we'll try to understand it in a different perspective. First, I want you to introduce to linked list. I don't want you to talk about the terms node and pointer as soon as now. I want you to think it with the help of a practical scenario. Just think you along with a group of friends went to a cricket match. Unfortunately, you have got seat in the first row. Your friend has got seat in the second row and so on. You have 10 friends and they are in 10 rows respectively. You have a cookie packet. You need to pass it only to your friends. What will you do? You just pass to the person who's in the second row if you are in the first row and he passes to the person who's in the third row and so on. So here if you just see from the first node, from you are trying to make a connection to the second person or the second data. That is, in this scenario, the cookies can be analogous to data and the persons can be referred to pointers. As you remember the place or location of the second person, you tend to store the address of the next data that is being stored. Literally, you store the cookies or you send the cookies. Similarly, you send the data to each and every location in the memory. And in the similar way, how you keep track with the help of remembering the location of the next person in the next row, you will try to keep track of the next location with the help of its address. That's how a linked list works. Let's look into its practical implementation.
As we have discussed, let's say I have stored the data of student 1 at a location of 100 and data of student 2 at a location of 200, data of student 3 at a location of 300 and so on. Linked list actually tries to keep track of all the data by pointing to the next memory location, and this pointing is done by storing the next memory location at the current state or the current node. So it stores 200 here and this actually stores 300 here. If this is the final entry, then it points to the null pointer. Whenever we come across null pointer, that actually indicates the end of the list. For example, we have taken the details of all the students and a new student wants to join our school. So we need to collect the data of this student and also keep track of it. As you have seen, the registration number which was given to the student is 2, but we have someone at that place now. So if I want to do this, I have to actually insert this block of memory in this position. For doing that, I can actually make it point to this location, and if this points to the next location, automatically the numbers will be adjusted. Now this is the first block, this is the second block, this is the third block and so on. If you might have seen, by making a couple of changes in the address, if this is at a location 250, let's say, instead of 200, we have stored 250 here, and at the end of it, as the next address is 200, here we have tried to store 200. By making a small change, we have actually incorporated a new student successfully. Let's take one more instance where this new student is not happy with our school and he wants to leave. So his details are no longer required and can be eliminated. For this, I just need to make it point to the previous node. When I change this address and I revert back to 200, this actually points to this location and this link will be erased. As we start with the starting address, from here I am reaching the second student and from there I am moving further. So there is no track of this student and the memory which is allocated to this student or his details can be removed from our system. We need to observe that in the case of practical scenarios, especially in the real world scenarios, the situations like this will occur very frequently and it is very easy to keep track of them with the help of linked list. Suppose, for example, if you have used arrays to store the information of the students, let's say we have used an array of structures. We know that structures is used to group all the details. So we have used a structure to group all the details of a student, and we have used array of them: student 1, student 2, student 3. Now a particular student 2 wants to enter our school. His details has to be filled. All the elements which are after 1 has to be moved to the next location, and this has to be inserted at this place. There are two factors here. First one being availability of memory, and second one is costly operations. The same happens even in the case of deletion. Suppose if this student has to be removed, all the student details which are after that has to be moved to the forward location. So if we try to use array of structures, or if we try to work with array data structure in real world scenarios, it may not work always. That is why we try to use linked lists. Let's have a quick recap. Why are we using linked lists? First one being lack of contiguous memory locations. For example, if you take an array and if you want to store the details of 100 students, and one student, let's say, is taking 10 MB, we know that array actually looks after contiguous memory locations. It is difficult to find size of 1 GB continuously. In that case, linked list can come to our rescue. We can actually allocate a memory block at an instance, and we can point to the next address where another details can be stored. As we have already discussed, insertion and deletion is also a factor. So in the real world scenarios where people tend to use insertion and deletion a lot, linked list is having more advantage over arrays. And also it is dynamic data structure. You can allocate the memory whenever it is required with the help of malloc, calloc or realloc library functions.
Right now, everything seems so positive about linked lists. But if it is the case, why do arrays exist? Why we have not replaced arrays completely with linked lists? Let's have a look.
Even linked list is having some disadvantages. First one is extra space for memory location. If we just observe, we are trying to store the data, and then we are also trying to store the next memory location. So the location at which this is stored is also being stored. That is, we are allocating extra space for storing memory location of the next element, which is generally tend to wastage. And it is possible to have only sequential access. Let's take a linked list and an array. If I want to access this element, I can access it directly with a of 1. But if I want to access this element, I have to start from the beginning of array and I have to go in sequence. That is the only way. And the address of the first node is actually represented in a head pointer. So head pointer actually provides us the entry to the linked list, and then we'll move further. If we have lost head pointer, then we cannot actually keep track of any node and the entire list will be at stake. This is a disadvantage of the linked list, and it is also not cache friendly. In the case of array, while you are dealing with a particular word, it's most probable that you may deal with the next word because of the locality of reference. So you store all of this in the memory or in the cache. But in the case of linked list, as each and every one of them are at different memory location, it is not so cache friendly. Understanding linked list, I think it's time to deal with linked list insertion. Suppose to create a linked list, we actually need a node. The node will be having the data. This data can be anything. It can be a single integer, or it can be a structure itself which contains many other data types or variables, or it can be character, anything, or it can even be array of integers or array of anything. Literally we can store any sort of data, but we need to also note the memory location of the next block. Now, if you have observed closely, here I need to group data and also the memory location. So, when it comes to grouping two things, we know that we have to use a structure. Let me try to declare a structure, and I call each and every one of it to be a node. Let's name it node. I am creating a structure whose name is node. For the sake of simplicity, I am taking data to be a single integer. So, I declare an integer data. And I need to store the address to the next block, that is a pointer, because we are trying to store the address and we know that pointer is a special variable that tends to store the address. So we can store it, and it is of the type the same structure. So struct node pointer which points to the next address. So by declaring this, you have actually created a structure which has grouped data and which has grouped a memory location pointer. But the memory has not been allocated. You have defined only the structure. I have already told you the memory to a structure will be allocated when you create an object, or if you create it with the help of a pointer, you have to allocate the memory with the help of dynamic memory allocation libraries, that is CLOC or MLOC. After defining the node, let's try to write a program where we are making a linked list. First, to make a linked list, we need to create a node. For creating this node, I have to create an object to this structure. Let me try to create an object to this structure. So this has actually created a pointer and memory has not been allocated yet. Let's try to allocate the memory with the help of malloc library function. Memory has to be allocated and the size of the memory that has to be allocated should be equivalent to size of this node. So size of struct node, and it returns a pointer to start address that has to be typecasted to struct node pointer. So struct node pointer has to be written here. After this statement, memory has been allocated and the start address will be returned to pointer. We know that the first memory location inside the list is called head pointer. So instead of calling it P, it's better if we call it head. And we know that this is the pointer. If I want to access the data for this pointer, I can access it with star head dot data, where I tend to fill the data, or I can even write it as head arrow data 5. So it has created a node and the memory is allocated after this statement, and you have tried to access and store the data 5. There is only one value in the linked list as of now. As the end of the linked list should point to null, we have to make head arrow next to be null. In the similar way, you can actually create different nodes, and this procedure is same for all the nodes. First you have to define a node structure, and then followed by you need to define a pointer, and you need to allocate the memory with the help of dynamic memory allocation libraries. After this, you can access its data members with the help of arrow operator, and then you can actually try to build a linked list. Let's say I have made a linked list and it is having these pointers 1, 2 and 3, and it is pointing to null. Now if I want to insert 0 in this and I want to insert at the beginning, we know that each and every node is having a memory location. Let's say this is at 100, this is at 200 and this is at 300. These memory locations will be stored at respective positions. Now 0 has to be inserted here. For that, I just need to do one thing. I need to store this address at this location, and I need to make this as head pointer. So if we have a head pointer which is already declared, then I have to create this node initially. I need to set the value to 0 and I need to set the memory location as head. Let me just divide it into steps and let me just do it. The first one, I have to create a node. For that, I have to create an object. I have created a pointer object and memory has not been allocated. So let me try to allocate the memory with the help of malloc. T is equal to, and I am trying to allocate the memory which is equal to size of the same structure. And as it returns a void pointer, I am trying to typecast it. Struct node pointer. Now the memory has been allocated after this step, but nothing has been accessed. So let me store the data and let me set it to 0. T arrow data, I am setting it to 0. Now the data has been set to 0, and as of now it is having only one node. Let me point the next pointer to null. So this points to null. You need to remember that 3 basic steps. These are the steps which are repeated in every linked list program. If you just try to understand this, then each and everything will be falling in its own place. Now, after creating the node and after accessing the data, it's time that we add this inside this linked list. We know that this is stored in head pointer. To make it the first node, this actually needs to store this address. So this actually can be accessed with T arrow next, which should be equivalent to head. I can write it with T arrow next equals to head. This actually points to this location and 100 will be stored here. After this, I need to change the head. We know that head is always the first node. This is T as of now. So head has to be changed to T. After doing these steps, we have added 0 to the list. Now the list is as follows. Let's say these are at locations 100, 200, 300, 400 respectively. If you want to insert a data, suppose 7, this has to be inserted at this position. So first you have to create a node, maybe with a pointer. Second, you have to allocate memory. Third, access data and next pointer. After these 3 steps, the node has been created and it has been pointed to null. All these steps have been discussed previously, and if you want, you can refer to the previous steps for reference. Now, let's say this has to point after 1. For that, we know that we are actually having access only to head pointer and nothing else in the list. Head pointer is actually at 100. If I want to move to this location, I can move by making it to head arrow next. As head is 100, 100 arrow next refers to this location. This location is actually 200. So 100 arrow next will give me 200. As I have already told you, the only way to enter the list is through head pointer. So if you lose head pointer, you cannot access this list later on. Then it's better to make another pointer to the head pointer. Let's say you have made another pointer P which is pointing to head. And if you want to manipulate head pointer, you can manipulate with the help of this P pointer. By this way, you are having head safely and you can access the list whenever you want. After declaring a pointer and it is pointing to head, I need to move it to the next location. So P is equal to P arrow next. We know that P arrow next is 200. P is initially 100. After this statement, P actually becomes 200 and P moves here. Now, this content has to be modified and this has to be changed to this address. But if you do this initially, if you make this to point to this, the value which is present at this location, which is 300, will already be lost. So, the first step is first take this address and make 7 to point to this address. So, this address can be accessed by P arrow next. 300 which is present at this address, P arrow next has to be stored at this. Let's say this is T. It can be done with T arrow next is equal to P arrow next. So, T arrow next here 300 will be stored. After this, the value at P arrow next can be modified to T. So, P arrow next can be changed to T. And let's say if T is at a location of 700, the value will be changed to 700. After executing all of these steps, you'll start with head pointer, you'll move here, the next address is 700, it will go to this location, the next address is 300, it will go to this location, here 400 will be stored, it will be moved to the next location and so on. Just try to understand the sequence of steps. If you try to change the value without taking a copy initially, it will actually lead to the loss of the list. So just try to write the list with the help of this pointer representation. Just check all the steps that have been given. Whatever is the best feasible way where you have retained the entire list, you have to go in that sequence. Sequence is very important and which can be easily understood by just trying to write this pointer representation and trying to trace each and every step sequentially. Let me just try to tell you how deletion occurs. I think with the help of this you can actually look after deletion, but let's go through a quick example. Let's say the linked list is having the following elements. Now, if you are having the head pointer here at a location of 100, the next location is 200, 300, 400 and finally null. If you want to delete the last node, we know that the access to the list is only through the head pointer. So, we cannot modify the head pointer. I am declaring another pointer. Let's say to be temporary pointer T. T is equivalent to head. This actually points to this location. Now, I need to delete the last node. For deleting the last node, I just need to point the last before node to null. If this points to null, then this node will be automatically eliminated. So, let's see how we can make it. If you want to identify the last node, you can identify this by this statement. If this is a node n arrow next is equal to null, then it is a last node. As we need to reach the last node, we can actually shift or check for the condition till the node arrow next becomes null. As it is T, while T arrow next. If it is not equal to null, if the last node has not been reached, just move T. T is equal to T arrow next. So, T is initially at this location. Now, T arrow next is not equal to null. So, T moves to next location. T arrow next is not equal to null. So, T moves to next location. T arrow next is not equal to null. So, T moves to next location. Now, T arrow next equals to null. This condition fails. So, it comes out of the loop. Now, we actually need to make this point to null, but we don't have any pointer to it. So, let's take one more pointer initially, that is P. And P is also pointing to head. And I have changed the value of T initially. T is equal to T arrow next, but I am keeping the P as it is. And P is equal to P arrow next. I am also changing it. That is just because I am trying to keep one pointer here and one pointer here. And I am trying to increment each and everything one by one till the last node was encountered. When it has reached the last node, P will point to the last but one penultimate node, and I can modify its address to null. Let's just trace it. Initially T is pointing to head, okay, and P is also pointing to head, okay, fine. Now T is equal to T arrow next, so T has been moved to the first node, but P was still there, while T arrow next is not equal to null. Whether T arrow next is equal to null? No, right? So this condition is true. So P is equal to P arrow next, P comes here, T is equal to T arrow next, T moves here. After this, whether T arrow next is equal to null? No, right? So T moves further and P also moves further. Now, whether T arrow next is not equal to null, this statement is failing and it comes out of the loop. After it comes out of the loop, just see, P is pointing to the penultimate node and T is pointing to the last node. If you want to retrieve the data of the last node, you can retrieve with the help of a T. So if you want to take the data into an integer k, then the data can be taken from T arrow data. Now you want to eliminate the last node. The penultimate node can be made pointing to null. P arrow next is equal to null. This actually makes the penultimate node point to null. In this way, you can actually insert or delete at any required position by just keeping track or understanding it with the help of this representation. This is how the linked lists are generally dealt with. Before winding up, let's try to understand types of linked lists. We have single linked lists that are normal linked lists where the end node points to null. We have doubly linked lists where we are having the previous pointer and the next pointer. The first node of the previous pointer points to null because that is the first node. The next node points to the second and it actually stores the first because of pointing to the previous location. And the last node actually points to null. These are the single and doubly linked lists. In the case of single linked list, you are storing only the next address, but in the case of doubly linked list, you are storing the previous as well as the next address. And in the case of circular linked list, you are having two things. First one is single linked list and also doubly linked list. In the case of single linked list, everything will be same, but as it is circular, the last node will point to the first node. In the case of doubly circular linked list, everything will be same as doubly linked list, but the last node points to the first node and the previous of the first node will point to the last node.
Now we have seen a lot about linked lists. Insertion, deletion of a node, writing a linked list from the scratch and how to maintain it a lot. So have you thought about stacks and what are their practical approach? Have you ever thought the applications like Paint and your web browsers work with the help of a stack? Stay tuned to find out.